Let's revise particle physics. This video will be following the AQA physics specification. So, starting off with atomic structure. The basic structure of an atom is that it has a small nucleus located in the center, and that contains some protons and some neutrons. We have electrons which are sort of orbiting the nucleus around here. In reality, they're following this amazing probability density cloud, but more on that later in quantum mechanics. Most of the stable visible matter in the universe is made out of these particles, and they have separate properties. For instance, the proton has a charge of plus 1.6 times 10 to the power of minus 19. The neutron has no charge, and the electron has a charge of minus 1.6 times 10 to the power of minus 19 coulombs. You can see the masses of the particles as well here. We can see that the neutron is just ever so slightly heavier than the proton. Actually, in an exams, typically they might be given just up to 3 significant figures. If that's the case, both the proton and the neutron have a mass of around 1.67 times 10 to the power of minus 27 kg. The electron has a much lower mass of around 9.11 times 10 to the power of minus 31. We're going to be using those in physics quite a lot, so we'll probably end up remembering those values. You may also come across a notation that talks about the relative charge and the relative mass. In those units, the proton will have a relative charge of plus 1, the neutron will have a relative charge of, 0, and the electron a relative charge of minus 1. We could also talk about relative mass. In this case, both the proton and neutron are going to have a relative mass of 1 because they have roughly the same mass. The electron, though, is multiple times smaller, and its relative mass is tiny. It's about 0.30, so it'll be 0.005. So how can we express this with symbols? Well, imagine that we have some sort of an element, let's call that X. This element will have a certain number of protons, and we typically write these in this corner over here. The proton number is often given the symbol Z. There's also the total nucleon number, which is given the symbol A, and we typically write this down right over here. So let me give you an example. Let's pick helium, for instance. So this over here is my artistic drawing of a helium atom. The number of protons in a helium nucleus is, 2, so this number here will be 2. Because there are 2 neutrons as well, the total nucleon number A is the number of protons plus the number of neutrons, so this here is going to be just 4. It's important to define that this number here, the proton number, actually defines a chemical element. Let me give you an example. So let's say that we have hydrogen. Let's say we have hydrogen 1, which is just 1 proton. We could also have deuterium, which is still hydrogen. It has 1 proton, but it also has a neutron. So in the nucleus, so let's say that this is the nucleus of hydrogen 1. The nucleus of hydrogen 2 will just be a proton and a neutron. This number here is the total nucleon number, which was now going to be 2 because there's 2 particles in the nucleus. You could also have hydrogen 3, which will just be a proton, and 2 neutrons like so. This is known as tritium. And those particles right here are actually examples of isotopes. So an isotope will have the same number of protons but a different number of neutrons. Isotopes have a lot of applications. They're used in medicine. They're also used in radioactive carbon dating, which I'm sure you've heard about. And let's use that as an example of a use of isotopic data, which is part of the AQA spec. So, for instance, radioactive isotopes can be used to calculate the age of objects. Now, how does that work? So, all living things or all living beings contain the same ratio of carbon-14 to carbon-12. Now, carbon-14 is actually radioactive, and we actually breathe in some radioactive carbon-14 from the atmosphere. How is that produced? It's produced by cosmic rays, which essentially strike the atmosphere of the Earth. Imagine that this here is the Earth, and they can cause some reactions, which means that over here we can have some carbon-14 that's been created after interactions with a cosmic ray. This diagram is obviously not up to scale, by the way. Now, we actually have a constant ratio of carbon-14 to carbon-12 in our bodies. And after an organism dies, for instance, a tree, the carbon-14, well, the ratio of carbon-14 to carbon-12 starts to decrease. Now, physicists can use the percentage of carbon-14 left and compare it with isotopic data, a really important word, to actually calculate the age. There's another formula that we should know, and that is the specific charge. This is just the ratio of the charge of a particle divided by its mass. We can also see from this formula that the specific charge will just be measured in units of coulombs per kilogram. If we're dividing by mass or by kilograms, we often write this as kg to a power of -1. Well, let's do a little bit of an example. Let's pick a particle. So shall we just start off with the proton? And what is the specific charge of the proton? Well, in order to find that for the proton, this will be equal to its charge, which is 1.6 times 10 to the power of -19 coulombs. And we're going to be dividing that by the mass of a proton. So we'll just use 1.67 times 10 to the power of -27. Let's put this into a calculator, and up to, let's say, 3 significant figures, or let's use 2, we're going to get around 9.6 multiplied by 10 to the power of 7 coulombs per kilogram. Now let's see what makes nuclei stable or unstable. In order to do so, we need to think about what are the forces inside of a nucleus, and ultimately we need to discuss the strong nuclear force. So imagine that this over here is just a nucleus, so the red particles are protons, these blue particles, let's say, are neutrons. So what forces are acting on the nucleus? First of all, we have the force of gravity, which is trying to pull all these particles together. This is actually very weak, as we're about to discover in this course. So Fg will be pointing somewhere towards the center of mass. Now there's going to be another force acting between the charged particles. And remember, because the protons are positive, two positive particles will repel. So there's going to be another force, and this will be the electrostatic force of repulsion, which will be very, very large indeed, so much that I can't actually draw this vector out properly. Now, if those were the only two forces to exist, this means that matter would just separate out, and this particle would just fly out, and this particle here would also fly out, because they are repelling each other. Now they don't, which means that there needs to be another force that exists within the nucleus that is gluing the nucleus together, and well, this force is the strong force that is responsible for bringing and gluing in the nucleus together. Now, interestingly, if the size of the nucleus goes beyond the 3 femtometers, we're very likely to receive a decay particle, or to see a decay particle. This is because the strong nuclear force can only act within this region. So look at that. At the moment, I've only drawn 4 particles, but what if we had 238 particles? This is one classic alpha decay of uranium 238. So this will actually emit an alpha particle and it will decay to thorium. So thorium will be element 19 because it's losing an alpha particle, which the alpha particle is just 2, 4. This means that our nucleon number is going to be 238 take away 4, which is going to be 234. And this right here is an example of an alpha decay equation. We're emitting an alpha particle and we have a conservation of all the numbers. Our proton number is conserved, so 92 is equal to 90 plus 2, and our nucleon number is conserved, so 238 is equal to 234 plus 4. Particles can also decay via beta minus decay. So this one here was alpha. Let's see what beta is. So in order to do so, let's have a look at the decay of, let's say, carbon-14. So carbon-14, as we said, that is radioactive, and it's carbon-614. Now this actually decays to nitrogen, which has a proton number of 7 and a nucleon number of 14. In order to do so, we need to keep all the numbers, all the fundamental numbers in this equation constant. So for instance, the relative charge here is plus 6 on the left hand side, however on the right hand side is plus 7. So the only way we can do that is if we have a beta particle come out as well, and this beta particle is actually a simple electron which has a relative charge of -1, nucleon number of 0. And our equation is balanced. Now this is an example of beta decay, however this is not complete. Experiments showed that the energies or the total mass energy on the left hand side was not equal to the total mass energy on the right hand side. So scientists hypothesized another set of particles called a neutrino, known as the electron neutrino actually, and this is actually an antiparticle in this reaction that must occur. And this is an example of a beta minus decay equation. Have a look at something incredible. The total number of protons here is 6, whereas the total number of protons here is actually 7. So by the power of something called the weak nuclear force in beta minus decay, a neutron has turned into a proton. So an actual neutron turns into a proton. A couple of tips to remember: every time we have a beta minus decay equation, obviously we get the beta particle, which is just an electron. The nucleon number will always remain the same because a neutron will turn to a proton, meaning that this number here is constant, and this number, the proton number, will always go up by 1. We're also going to get the antineutrino. I'm going to be talking about antiparticles next. However, a good rule of thumb to remember is that if you can see this dash here for the minus sign, you can definitely see an antiparticle. An antiparticle is signified by this dash at the top of the particle. So in physics, each fundamental particle has its own antiparticle. How amazing and incredible is that? For instance, the electron has its antiparticle being the positron, the proton has its twin antiparticle, which is the antiproton, the neutron and the antineutron, so on and so forth. Now, how do the properties differ? First of all, the mass is exactly the same. So for instance, both the electron and the positron have a mass of 9.11 times 10 to the power minus 31 kg, and the positron also has a mass of 9.11 times 10 to the power minus 31 kg. And this is where things start to get really interesting. The electron has a charge of minus 1.6 times 10 to the power of minus 19 coulombs, but the positron has a charge of plus 1.6 times 10 to the power of minus 19 coulombs. So in short, each antiparticle has the same mass, and let's write this down over here. So antiparticles have the same, exact same mass, they're the same particle, but they have the opposite charge. Let's compare the properties of the other particles. So for instance, the proton and the antiproton, they have the exactly same mass as we said, but the opposite charges, so plus 1.6 times 10 to the power of minus 19 and minus 1.6 times 10 to the power of minus 19. The neutron and the anti-neutron, so they have the same mass, 1.675, tiny bit larger than the proton, and they actually have the same charge because the neutron has 0 overall charge and the anti-neutron has once again a 0 net charge. People often ask me, why are those two particles different? The answer to this will become apparent once we start doing quarks. They're actually a different particle. They made out of anti-quarks instead of quarks, and it just turns out that the properties are such that the net charge is 0. They also have an opposite spin, which is another property that we don't really do much of during A level. We actually need to know about one more particle in our exam, and this is of course the neutrino. So let's just write this down as the neutrino, and the symbol for an electron neutrino is just this. It has a tiny mass. It's very close to 0. It is just above 0. It's not actually massless though, so I'm not actually going to write 0. Loads of textbooks write 0, so we can just say that the mass is basically negligible. So we'll just write negligible. And it does have a charge of 0 though. Now the symbol for the antineutrino is such, and it has exactly the same properties. So it has negligible mass and it has a charge of 0. Now let's have a look at another property which is very useful for particle physicists, and that is rest energy, that is typically measured in mega electron volts. If you're wondering where on earth does this unit actually come from, the mega electron volt, we're going to do this later in the course, but basically electrical energy is equal to the amount of charge multiplied by the voltage. So if our voltage is, let's say, the electron, or if our charge is the electron charge and our voltage is the voltage that we've applied, let's say a volt, we can get the unit of 1 electron volt. In this case, a mega electron volt, we're also going to have a factor of 10 to the 6 right over here, but this is just a unit of energy. So those two particles, which are the electron and the positron, should just zoom out a little bit, they actually have an energy of a rest energy of 0.51 mega electron volts. The proton and the antiproton around 938. For the neutron and the anti-neutron, it's around 939, so just a tiny bit higher. Just for comparison, recently at the Large Hadron Collider, and I'm filming this video in 2022, they reached an energy which was 13.6 tera electron volts, and this is the current record, I believe, unless the OHC has managed to go above that in the last few weeks, but as far as I know, it's 13.6 tera electron volts is the maximum energy that we've smashed particles together. Now, in order to explain the next part of particle physics, we need some understanding of the photon model of EM, or electromagnetic radiation. Electromagnetic radiation is actually made from particles of light which are called photons. Now, light has wave-like properties such as diffraction, interference, etc., but it really is a particle, and each of those fundamental units of photons have energy given by the following. The energy is proportional to their frequency, and the constant of proportionality is known as Planck's constant, which is one of the most fundamental constants that we know of. And the value of Planck's constant is actually very, very small, 6.63 multiplied by 10 to the power of minus 34 joule seconds. The wave frequency is linked to the wavelength. It's just given by the wave equation, which is, of course, that, let's just zoom in a little bit, that the speed of light or of any wave-like feature is given by the frequency multiplied by the wavelength. So let's just write the wavelength like that. This, of course, means that the frequency is just equal to the speed of light divided by the wavelength. And we can take this equation and we can sub this into here. We can get our second equation for the energy, and that is that the energy is equal to Planck's constant around the frequency. I'm going to write C over lambda. And just to summarize, we can also write this as E is equal to hf. And this here is the energy of a single particle of light known as the photon. There are two equations for it. So the reason why we covered the photon theory is because we want to understand annihilation. So annihilation occurs when an antiparticle meets a particle and all the mass gets converted to energy through this process. Imagine that we have this electron over here that meets a positron. All of their masses are going to get converted to photon energy. So this photon here that is coming out will have a certain energy. We can call that some sort of a minimum energy. Let's call that E minimum. And this one here will also have some energy, which is E minimum. We can use energy conservation and actually estimate the wavelength of these photons. Because this here was a minimum energy, the wavelength will actually be a maximum. So how can we actually calculate the maximum wavelength? Let's call that lambda max. Well, remember, those particles, the electron and the positron, have some rest energy. Typically this will be given in the question, but in the table a few slides ago we mentioned that this was around 0.511 mega electron volts. So this means you can think of this as our input energy, and twice that amount, so twice times 0.511 mega electron volts is times 10 to the power of 6, and the electron volt is 1.6 times 10 to the power of minus 19. And this is our input energy. We can set that equal to the energy afterwards, which will just be the energy of the two photons. So we can say that this here will be equal to twice the energy of a photon. But what is the equation for the energy of a photon? Remember, the energy of a photon is equal to just hc over lambda. So rather than energy of a photon, I can literally just write twice hc over lambda, where h is Planck's constant and c is just the speed of light, like so. Now all I need to do now, I can actually cancel out those twos, is to rearrange for lambda and then plug in some values for h and c. I'm going to have my answer. After rearranging, we can see that lambda is 0.511 times 10 to the power of 6 times the electron charge divided by hc. Now let's plug in some values. So we know that h is Planck's constant, just 6.63 times 10 to the power of minus 34 joule seconds, multiplied by the speed of light, which is 3.0 times 10 to the power of 8 meters per second. And this here is, of course, the maximum wavelength. Plugging those numbers into a calculator, we're going to get a number around 2.43. So 2.43 multiplied by 10 to the power of minus 12 meters up to 3 significant figures for the maximum wavelength. The opposite of annihilation is known as pair production. Now, in annihilation, we had two particles meeting up and producing photons. In pair production, we have a photon which turns into a particle-antiparticle pair. Isn't the world of particle physics strange and great? We just have this particle of light which is just spontaneously turning into a particle-antiparticle pair. Now, the minimum energy for this to happen is that the energy of the photon, or the minimum energy of the photon, which once again is given by hf or hc over lambda, that has to be equal to at least twice the rest energy of the particles. This is typically given by E naught, by the way, so we can say that E min is equal to twice E naught. For calculations, we can also, of course, use that E min will be hf or hc over lambda. Let's talk about what a fundamental force is. Most of the forces that you'll be familiar with are not actually fundamental forces. So let's take an example, something like, should we just say friction? So imagine that we have something like a ball which is rolling with a certain speed v. This speed will be continuously decreasing due to a frictional force acting in the opposite direction of the movement. And what actually causes this force? Fundamentally, this force is actually an electrostatic repulsion force. The surface of the ball is not perfectly smooth. There'll be some electrons right on the outside, and there's going to be some electrons right over here. And this is ultimately an electrostatic force because the overall force can be broken down to the individual repulsion by those electrons, those electrons, those electrons, and those electrons all added up. Now, if we were to try and break down forces further and further, there are only 4 fundamental forces. The electromagnetic force, the weak nuclear force, that's responsible for nuclear decay. So shall we just write this down? Nuclear decay. The strong nuclear force, which we talked about in the beginning of this video, this holds the nucleus together. So let's say it holds the nucleus together. And of course, we also have gravity. Now, gravity is considerably weaker than the other 3 interactions, and we tend to ignore that in particle physics relatively often. We still don't have a quantum gravitational theory or a quantum theory of gravity, which is one of the holy grails of physics that some of the brightest minds in the world are actually working on. Here are 2 electrons. We can see that they're negative. What do the 2 electrons do? Well, they actually repel. So this means that there's going to be a repulsive force acting in this direction on this electron, and there's going to be exactly the same but opposite repulsive force acting on the other electron. How do the 2 electrons know to repel one another? Well, it turns out that the interaction is actually carried by a particle which is being emitted and exchanged by the 2 electrons, change of a particle which is known as a virtual photon. And actually, the electromagnetic interaction is carried out by this virtual photon. Now, an exchange particle for any interaction is known as a gauge boson. So should we just say over here that this here is just an example of an exchange particle, and they're different for the interactions that we know, and I've listed them down here. So let's have a look. So as we said, for the electromagnetic interaction, the exchange particle or the gauge boson is a virtual photon, and the EM interaction will affect all charged particles. There's also the weak nuclear force, which is responsible for nuclear decay, and the exchange particles there are W plus and W minus bosons. This can affect all particles. The strong nuclear force is exchanged via the pions, which could be the 3 types actually, pi plus, pi minus, depending on their composition. There's also the pi zero particle. The strong nuclear force, importantly, will affect only hadrons, particles that are only made up of 3 quarks, such as the proton or the neutron. The fourth fundamental force in our list, gravity. We don't yet have a exchange particle for it. There's a hypothesis about the particle known as the graviton. Talking about gauge bosons, by the way, lots of students often ask me, what are virtual particles? And the answer is that they are real particles really that exist for a very short time. And on to Feynman diagrams next. The trick is to always think about the y direction as time, what is actually physically happening to the particles. Let me give you a simple example looking at electromagnetic repulsion. So we're going to start off with a couple of particles which are going to be repelling each other. So shall we just choose two electrons represented by straight lines, kind of like this, and this is one electron. Let's label this as E minus, which is going this way, and we're also going to have another electron which is just up here, which is E minus. As I said, the two particles are going to repel each other, and we can represent this like so and like so. We can add in some directions and label the particles after this interaction as well. Something must have caused that repulsion, and what's actually caused it is a gauge boson, which represent with a squiggly line, and this is indeed just a virtual photon. And this is our first Feynman diagram. Another diagram that we need to know is that of beta plus decay. In this type of decay, a proton will turn into a neutron. This happens when the quarks inside of the proton actually release a W plus boson, and subsequently the W plus boson will turn into a positron and a neutrino. The equation for this reaction is that a proton will turn into a neutron plus a positron plus a neutrino. Notice how charge is balanced in this reaction. For instance, the overall charge on the left-hand side is 1. The neutron has no charge. However, the positron has a positive charge and the neutrino has no charge. So all the numbers on the left and on the right, top and bottom, are fully balanced. And here is beta minus decay. A neutron can turn into a proton with the release of a W minus boson, which will then turn into an electron and an anti-neutrino pair. What would the equation for this reaction be? We're starting off with a neutron. The neutron is of course 0, 1, and this will turn into a proton, which is just 1, 1. And now we have a little bit of a problem, because on the left hand side the overall charge is 0, on the right hand side the overall charge is 1. So we need to balance this out with the addition of this electron over here. So we're going to have an electron which of course has a charge of -1. This number here is 0, the nucleon number. Then of course we're going to have the anti-neutrino, which is just 0, 0. A good rule of thumb to remember when this has the dash for the antiparticle is that if you can see a negative sign within the electron, this means that we're dealing with a anti-neutrino. One more Feynman diagram that we need to know about for the exam is that of electron capture. Here's the equation for this diagram. We have a proton which captures an electron, and the result is a neutron plus an electron neutrino. Here's our proton and our electron, and as time passes there's a release of a W plus boson, and the proton turns into a neutron, and we also have a neutrino left over. As particle physics progressed, we discovered hundreds of thousands of subatomic particles. We needed a way to actually classify them via the standard model. Let's have a look at some of the basic terminology and classification of particles. First of all, we need to know that hadrons are particles which are affected by the strong nuclear interaction. They can be split into baryons. Now, a baryon is just a hadron with 3 quarks and a meson. This typically has a quark and antiquark, as we're going to explain later on. An example of a baryon, for instance, could be just the proton, could also be the neutron. A meson, on the other hand, could be something like a pion. So we can just say that this here is a pion, and we've talked about these, so it could be the pi plus, pi minus, the pi zero, the carriers of the strong nuclear force. It could also be another particle called kaons. There's quite a lot of them, actually, and there's quite a few other mesons as well. The kaons as well, they're pretty similar. They have the K plus, the K0, and quite a few others. It's important to note that particles can also be described in terms of their baryon number. This is another quantum number which is represented just by the letter B, and for baryons this is equal to 1. So those particles over here, they're going to have a baryon number of 1, whereas for the mesons, well, because they're not baryons, they're going to have a baryon number of 0. And this quantum number is conserved in a very similar way in a reaction, similar to the way charge is conserved. For instance, baryon number should be conserved. So if we start with one baryon, this could be a proton or a neutron, this is conserved. It's also important to mention that baryons tend to be inherently unstable, and so far as we know, the proton seems to be actually the only stable baryon that we exhibit, even though loads of experiments are trying to find a proton decaying, but so far this has been unsuccessful. Another major set of particles are leptons. These are particles which don't interact with the strong nuclear force. For instance, the electrons or the anti-electron known as the positron are examples of leptons. The muon, should we just write their symbols here as well? So this is the symbol for the electron. This right here is the symbol for the muon, so it's just a particle like this. It's almost like the heavier cousin of the electron. There's also the electron neutrino, which is given like this, and we also have the muon neutrino, which has the subscript of mu. Just like a baryon number, you can also conserve the lepton number, so we can just say that the lepton number is actually conserved. The muon, though, being a little bit heavier, is unstable and it will eventually decay to an electron. Now let's talk about quarks. They are a fundamental particle, and baryons and mesons, i.e. hadrons, are made out of them. An example of this is the proton and also the neutron. They're all made out of quarks. Here are some of the properties of some of the quarks that exists. So for instance, we have the up quark, which is labeled with a U, and that has a fractional charge of plus 2/3 from the elementary charge. So that is plus 2/3 E. The down quark has a negative third. We also have the strange quark, which also has a negative of third. The anti-up is negative 2/3. The anti-down, just the opposite, and the anti-strange has just the opposite. Now, let me show you how the composition of, let's say, a proton, for instance, is made using the quarks. So this over here on the right-hand side is actually a proton. And a proton, as you can see, is just 2 U's and a D. And we can figure out the total charge. I'll just write the total charge on a proton. Now, the charge of an up quark is plus 2/3 E plus 2/3 E. And we also have a down quark, which is minus 1/3 E. So this together is equal to 4/3 E, take away 1/3 E, which equals 3/3, which is just E. So the charge on a proton is, well, plus the elementary charge. Let's do a neutron as well. So a neutron, on the other hand, is made out of 2 down quarks and also a U quark. So 2 D's and a U. Now the total charge on the neutron is going to be 1 up, which is, let's just write that the charge on the neutron is going to be equal to plus 2/3 E, and then we're going to take away a third E, and then we're going to take away a third E as well. And as we can see that this here is equal to 0. It's important to know that the composition of an antiparticle, such as the antiproton or the antineutron, should we just talk a little bit about the antineutron? It's going to have exactly the same composition, but opposite. So it's going to be made out of 2 anti-downs. Oops, we need to add some dashes over here to the antiparticles. It's going to be made out of 2 anti-downs and an anti-up. And if we were to add up those individual charges, we're still going to get 0. So for instance, the antineutron will be made of 2 anti-downs, as we said, which is going to be plus a third, and then the anti-up, which is going to be minus 2/3, which of course is equal to 0. It's also important to note that in quarks there are 2 more quantum numbers that are conserved. So we're going to be conserving the baryon number and the strangeness. So the baryon number is just a third, which makes sense because it's 3 quarks to make a baryon. So each individual quark is going to have a fractional baryon number of plus a third for normal matter, and minus a third for antimatter. There's another strange quantum number known as strangeness, which is 0 unless we're talking about a strange quark. Now the strange quark has a strangeness quantum number of -1, which is super interesting. It's a topic of a whole nother video. And the anti-strange quark has strangeness of 1. Finally, let's talk about one more point of the spec, and that is the decay of a neutron. So this is just the standard beta decay in which a neutron turns into a proton. Now remember, the neutron is 1, 0, the proton is just 1, 1, meaning that we're going to need an electron, so it's going to be -1, 0. And then we also have a anti-electron neutrino. Well, if we think about the actual composition of this, because the neutron is 2 Ds and a U, and the proton is 2 U's and a D, during this beta minus decay, a down quark would have turned into an up quark via the weak nuclear interaction, and also of course we get an electron plus the anti-neutrino. This was the final point that I wanted to make in this very long video, and the next part of the specification is delving into the beginning of quantum physics, and you need to have a look at this video right over here that will guide you through the quantum world.